Pablo Narvaez is the subject matter expert for NASA's Jet Propulsion Laboratory in flight spacecraft electromagnetic compatibility in magnetic environments. Pablo is the Vice Chairman of the Institute of IEEE EMC SC7 Committee on Aerospace and EMC. He represents the United States on International Organization for Standardization, ISO, Technical Committee 20, Subcommittee 14 for Space Systems and Operations, is the project lead for international standards in EMC and magnetics requirements and testing. Pablo has led the EMC magnetic efforts for many spacecraft and science instruments, including Galileo, Ulysses, Cassini, Mars exploration rovers, CloudSat, as well as several instruments flown on the Space Shuttle. He's currently overseeing the EMC magnetic efforts for Europa Clipper, Mars 2020, surface wave ocean topography, as well as some non-NASA projects. And I'll just throw in that I have worked in the trenches with Pablo on a couple of EMC tests out at JPL, and I don't think I've ever seen anybody work harder than this guy. So anyway, Pablo Narvaez, give him a warm welcome. Thank you.
So like John alluded to, the fact that I do have to move on to my next talk. So I'm going to go through some slides a little bit faster than usual. I may not have a Q&A, but I'm going to be roaming the halls pretty much this whole week. So you can stop me and ask me any questions. Please do so. So basically, my talk will be on shielding. And what I want to do is, at the end of my talk, I want to make sure you understand what electric shielding is all about and magnetic shielding is all about. So I want you to understand that, fully understand after the end of my lecture here. So I'm going to use the Juno spacecraft as an example of how we use shielding, both for RF as well as magnetics. And also I'm going to use other projects as an example of how we use shielding. Juno was launched several years back, August 5th, 2011, and arrived at Jupiter July 4th, 2016. And basically it had a suite of instruments, magnetometers, gravity science, energetic particles, and microwave radiometers. Very, very highly sensitive instruments, to the point where we had to make sure that all of our instruments worked copacetically with each other. And there was a lot to do with shielding to make that happen. Shielding was a key component in ensuring that all these instruments worked properly. So one of the microwave radiometer's key science goals was is actually to peer deep into Jupiter's atmosphere. I will be giving a talk, a demo session this Thursday at 9:30. Please do attend. I'm going to talk more about what we found. Jupiter's strong magnetic fields also made us think about how we protect our instruments against the high magnetic fields. Most of the instruments that we build here on Earth basically just have to survive at the half a Gauss or operate through half a Gauss. At Jupiter, we predicted that the fields were going to be 12 Gauss. We found out that there's 17 Gauss. So most of the instruments that we were flying there needed to be upgraded and modified to ensure that they could operate in these high magnetic fields. So I want to talk about magnetic susceptibility first, so you have an idea of what we have to shield against. So most spacecraft, most boxes, most everyday boxes have motors, mechanisms where you can actually have noise that could cut through typical loop areas and create back EMF, causing bit streams to be corrupted, as you could see here, and therefore increase your bit error rate or other malfunctions. Also, on typical spacecraft, we have reaction wheel assemblies, magnetic torque bars, spectrometers, RF switches, a lot of moving mechanisms with magnets or rotors that generate high AC magnetic fields. So this is what we had to design against. So the microwave radiometers have these very sensitive isolators that could potentially saturate in Jupiter's magnetic field or be interfered with by mechanical components like the ones I just mentioned earlier. And so basically, when exposed to external magnetic fields, the microwave radiometer isolators would change in gain and therefore not operate at their optimum condition. So magnetic issues. on the microwave radiometer. Sensitivity to magnetic fields, the gain of these receivers would be affected by the interactions of the magnetic fields. So we had to find ways to ensure that we kept these isolators from being impacted by both Jupiter's magnetic field, the reaction wheels, and other moving mechanisms. So we went back and looked at what we've done on Cassini's spacecraft. Cassini flew around Saturn, orbited around Saturn, collected scientific data, and just several months back, it plunged into Saturn's atmosphere and disintegrated. Basically, it was a controlled crash burn because we were done with the mission. But one of the major interference sources were these reaction wheels. These reaction wheels were used for attitude control. They were used to maneuver the spacecraft to point it at a certain direction, whether it was a Saturn moon or the rings around Saturn. But they moved and therefore caused very sensitive instruments to be affected by the AC magnetic fields generated by these reaction wheels. But more so, we also had a plasma instrument and a magnetometer sensor that were also affected. So we had this problem that we solved by actually encasing these reaction wheels with mu metal. So let me talk about RF and magnetic shielding. Basically, there are two aspects of this. There's magnetic shielding, where we want to increase the attenuation of magnetic sources by shielding them with high permeability material. And there's RF shielding, basically encasing electronic boxes so that they themselves don't generate the high amounts of electric fields. So I want to make sure you keep this in mind. As I go through, I'm going to be interchanging magnetic shielding and electric shielding on and off. So basically, I also want to make sure that you understand some of the basic definitions. Magnetic field strength is described as the external field where we're trying to shield against. Jupiter's magnetic field at 17 Gauss, the reaction wheel magnetic field at sensitive sources. And I want to talk about the magnetic flux density, really the field that exists within a material. Okay? And the magnetic permeability, which is really the ratio of the flux density over the field strength. Permeability is really the ability of the material to absorb and attract magnetic flux lines. So these are key components. Field strength, external, flux density within the material, and the magnetic permeability. So saturation is when a shield basically becomes saturated after absorbing the maximum flux lines crossing its sectional area. And attenuation really is the ratio of the external field to the internal field. It's really a figure of merit that tells us how well have we shielded an external field within a sensitive component. So basically, if you have a shield surrounding a sensitive component, the external field versus the internal field is really your attenuation. Okay? So one way to verify this is by exposing this shield to an external field and measuring whether with the magnetometer or Gauss meter the field internal to this shield. So basically what happens with how this magnetic shield performs, it basically attracts flux lines around its material and redirects those flux lines and leaves a void inside a magnetic shield. Okay? So inside the magnetic shield you may have a sensitive component which is protected against the external field lines so that the external field lines are drastically reduced inside. So basically this, we call this the magnetic shield. It's soft magnetic material, leaves a void and therefore protects sensitive components inside. So here's an example of a typical source in free space. If you put just a steel wall, basically a high permeability or high ferrous material, the flux lines then are attracted along the steel wall and then follow the flux back to its source. Magnetic field lines must start and end at the same location. So here, let's say for argument's sake, leaving north, following the steel wall, and then coming back down to its south end. So basically, flux lines have to close on each other. Here you could see that the high permeability, low reluctance path that the flux lines like to take follow this direction and back to its source. Here we have an actual steel enclosure enclosure. So now what happens is that these flux lines carry the flux around the steel enclosure and back out to its source. So again, leaving a void inside sensitive materials, sensitive components, and so forth. So what we're after is really a performance of that shield to be within a linear region of these magnetization curve. Here's a typical value for mu metal material, where we have a perfectly working shield that redirects all the flux lines away from the center void of this shield. But once reaching a saturation area, we lose the optimum performance of those shields because they become saturated. They can no longer hold those flux lines within the cross-sectional area of that shield. So we have to make sure that whatever's designed, that's maintained within the linear portion of the material. So again, magnetic shields are dependent on the permeability of the material. The higher the mu, the better they perform. So ferromagnetic materials can have permeability as high as 100,000. There's a material called met glass that can have a permeability of 1 million, meaning that it's a very effective, efficient magnetic shield. So basically, one of the things I want to make sure is that there appears to be confusion with magnetic units. There's Gauss, Orstedts, nanoteslas, gammas. So we typically try to stay with the SI units of Teslas throughout, but I will be using Gauss interchangeably. So again, the performance of a shield is really dependent on the thickness and the volume of that shield. The larger the volume, the thicker the shield, the better its performance. So here we have one of the microwave radiometer isolators that we had to build a shield around it to protect it against Jupiter's high magnetic field. So here's a proof of concept that we came up with. We used, again, mu metal, which is a high permeability material. And here's an isolator with a ferrite component that easily saturated when exposed to Jupiter's magnetic field, which we were able to simulate in our lab. So once we found out that this component, a key component in the microwave radiometer, could not operate in Jupiter's magnetic field, we encased it in this mu metal and were able to show that it could operate optimally. This was just a proof of concept. Then we went ahead and designed that shield around the isolator and increased the optimum field reduction inside the isolator. And here we have the isolator for one of the microwave radiometers, and here's our shield, high permeability mu metal shield that we designed and built around it. So facts: the thicker the shield, the more effective it is. Multi-layer shields, Russian doll type of approach of shielding, is much more effective than one shield. And again, the nature of that shielding material is important. The higher the permeability, the more effective that shielding attenuation is. Also, these shields are very, very sensitive. Any shock, any dropping of the shields will certainly reduce their effectiveness. So as you can see here, you can read through the list of do's and don'ts of shielding. But the main thing is that you have to make sure that you design it to operate in the linear region of its optimum geometry. So moving on to electric fields. Electric fields emanate out of typical electronic components. You basically power on a unit. If you have circuit boards with traces or wires, you basically have radiated emissions in the electric field. Here we have a Mars science lab called Curiosity, currently roaming around the surface of Mars. And it has a very sensitive UHF antenna. This UHF antenna operates at 437 megahertz. Very extremely sensitive. With having all these wires, all these cables, all these flex shields, all these boxes, electronic boxes around it, basically concerned us early on in the project, because we have to communicate with our rover to our relay assets orbiting around Mars. So any noise created by any of the cables radiating electric fields or boxes radiating electric fields could affect the performance of our highly sensitive receiver. So during during most of our JPL missions, we actually have very sensitive receivers so that we can communicate with these either spacecraft or rover assets. So we have imposed very sensitive, highly stringent requirements to ensure that any box used on that spacecraft or that rover have very low level radiated emissions. And therefore, we have to focus on the cabling and the actual construction of those boxes. So here you have a typical box that was delivered to us on Mars Science Lab, the rover Curiosity. And then when it was delivered, yes, all these shields were well shielded, but then we found out that there were slots, open slots. Look at this. This is an open slot. So this was an error on the design. Obviously, I must admit that. And when we saw that, obviously, they forgot to put a lid over this box. So we had to, for our testing, quickly improvise, and we added strips of highly conductive EMI tape, is what we call it. It's a RF cloth, highly conductive tape, to short out these slots. Because what we were actually experiencing was high amounts of radiated emissions coming out of these slots that affected the performance of our radio. So here you could see a close-up of those slots, those gaps that had been bridged over by the EMI tape that we applied. So basically, with fast rise times in our signals, our sensitive receivers see more and more higher harmonics of the noise created by these signals crisscrossing all of the boxes between drivers and receivers. So you have here, for example, and I want to thank John McCloskey for this nice picture, and I will continue to use John McCloskey's nice view graphs as well as Frank Lefrank's slides. But here you have a fast digital signal, and when you decompose that from the time domain into the frequency domain, you have all these harmonics composing this fast rise time bit, where you have its fundamental going all the way to its nth harmonic. Typically, we have high-frequency receivers that see these high harmonics more and more often. So if you have a receiver and a driver and a typical cable, and you push these fast, high rise time in the picosecond range signals, they tend to radiate and cause problems at higher and higher frequencies. These could be operating at 1 megahertz. We actually have seen harmonics up into the gigahertz range because of the fast rise times that these signals create. So on Mars Science Lab, we actually saw some of those signals affecting the performance of our UHF receiver. Here we have a requirement that all the noise coming out of our Curiosity rover had to be below this red line. What we ended up seeing were these spikes throughout. And so what happens is that a poorly designed box basically generates high amounts of common mode noise that invariably will escape out through its wires, its cables, and boxes and generate noise in receiver bands. As you can see here, here's a typical receiver band and a requirement. And all these spikes, all these emissions come out of these poorly designed cables or slots in a box. Here's one of our actual Curiosity cameras. When we turned on, in our UHF range, all this noise just jumped up. And as you could see here in one of our channels, we actually locked on, our signal locked on to that camera. And it was a false lock. And so one of the things that we had to do was shut off the cameras during our mission every time we communicated with the rover from our orbiting assets. So here you could see another camera turned on, and basically without the camera on, we had a nice lock to our receiver during ground testing. But as soon as we turned on the camera, our receiver locked onto that spur coming out of that camera, and we lost lock, as you could see here. As soon as we shut off that camera, our receiver locked back on. So again, poorly designed packaging of these cameras caused this receiver to lose lock. So a direct correlation between a poor design of our cameras, the packaging, the cables, and the fact that we were losing lock. We didn't want this to happen once we landed on Mars. There's no way we could then talk to our asset on the ground. So we had to come away with innovative solutions to fix that problem. So here you can see again, the camera's on. created all this noise, and our AGC, automatic gain control, fluctuated everywhere. So again, the cameras, because of the flex cables that were poorly designed, the packaging with gaps and apertures cost us direct issues with our communication receiver. So you could see here a poorly a signal carrying through a printed circuit board within a box, poorly designed, will dump noise onto the structure. That noise will then find its way, radiate it through wires or apertures on the box, and create a spectrum of noise across sensitive receivers. Here's an example of a requirement with a notch, and this is the noise coming out of a noisy box. This is what we want to avoid with the right shielding, the right approach to shielding. These are the things that need to be avoided. Not only on spacecraft, but also ground-based systems. This could be applied across everywhere. So a poorly designed system, here's a simulation of a poorly designed system, will basically corrupt receiver bands. A well-designed structure will reduce those emissions significantly to the point where you're not affecting the performance of receivers or other instruments. So again, a correct PC board layout will control those emissions to the point where you can minimize the radiated emissions. The packaging of that box is key. So why do we shield? I want to go in through that. Because more and more, there are requirements that are becoming more and more stringent. We're flying more and more sensitive instruments, more and more sensitive receivers, and the notches become deeper and deeper and deeper, so that we have to focus on shielding boxes at the very beginning, shielding cables at the very beginning correctly. So here's a typical box that we tested, and it operates at 1 megahertz. We measured it up to 1 gigahertz L-band. Here's the radiometer band, L-band, and we were able to see the harmonics of this 10 megahertz clock all the way in the gigahertz range, all the way at L-band. So it was incredible. So we had to correctly re-shield that box and fix it to minimize and eliminate these spurs. Otherwise, our radiometer would be affected. So the purpose of shielding is to contain emissions from noisy circuits, protect the signals carrying conductors from interference. And this is from directly from John McCloskey. The whole reason for the shield is to provide a return path of the source over its lowest impedance. So, courtesy of Frank Lefferink, so in shielding, for an infinitely large plate, basically you have an incident field which then hits a surface, a metallic surface. Some of that incident field will be reflected off that surface. Some of it will actually go through and get absorbed, and some of it will actually be reduced through multiple reflections. And eventually what gets through is that transmitted field. So the incident field with a barrier, metallic barrier, will get reduced, and the transmitted field will be lowered. Depending on the characteristics of this barrier, this transmitted field may be low, or if this is a poor barrier, this transmitted field may be high. So again, shielding of a large plate, basically we have a shielding effectiveness that is directly related to the shielding due to the reflection and the absorption of that shield, and then the multiple reflections. So there are 3 terms that make up the shielding effectiveness of that material. In practical situations, we can neglect the term within the material, but really the major component of the field reduction is due to reflections and absorption. So again, here you have the incident field crossing this metallic barrier. Some of it will be absorbed, some of it will be reflected. Okay, and this barrier, and how effective it is really dependent on the permittivity, permeability, and the conductivity of that material. So here's, again, typical equations that make up the reflection term and the absorption term. The absorption term really is related to the thickness of that material, as well as the material itself is made up of the conductivity and permeability and the permittivity. Think of those as key terms. So the thickness of that material and the skin effect of that material it gives you the absorption term. The skin depth really is related by this equation, right? And it's inverse related to the frequency, okay? Which results into this equation. So at lower frequencies and at small thicknesses, this absorption parameter is quite low. For the reflection term, you start off, even though it's related to inverse of the frequency, you start off at high reflection terms, and it just, as a function of frequency, is reduced, is lowered. And again, the absorption term is related to the thickness of the material as well as the square root of the frequency. So this increases as you increase in frequency for a given thickness of that material. So the shielding effectiveness is made up of these two terms, the reflection term and the absorption term. The reflection term starts off high and reduces as the inverse of the frequency, and the absorption term starts off low for a very thin material and then increases as a function of frequency. So here it is. Here is the absorption term, which starts off low and then takes off exponentially for higher frequencies, and the reflection term starts off high and then decreases as a function of frequency. When you take these two together, you have a very good shielding effectiveness. This is for a 1 millimeter thick copper. So you start off high and it just takes off exponentially. So for a very large infinite plate, the shielding effectiveness is through the roof, literally 250. Who wouldn't want 250 dB of attenuation? However, this is for an infinitely large plate. And so, yes, we have an extremely high shielding effectiveness, but for the fact that it's for a large plate and because it's for plane waves and for far fields, we really can't utilize this for what we do in everyday life. Most of what we do is at very, very close distances. So because we're at short distances, our clocks are right next to a shield container. Our converter frequencies are also, our power supplies, chopper frequencies are very close to the box wall. So we have to find out what type of that source is and the distance of that source to the wall. So we have to find out what that wave impedance is. And for electric dipoles, for example, a wire, a floating wire or a strip line, the wave impedance for that electric dipole is very, very high. For a magnetic dipole, for example, a loop antenna on a circuit board, a motor like the ones I showed earlier on, those are very, very, have very low wave impedances. So we, in the near field, okay, we have electric dipoles, high voltage, low current, of high wave impedance, and magnetic dipoles, solenoids, transducers, solenoids or motors with very high current, low voltage, we have a very, very low wave impedance. Again, because wave impedance is volts per meter over amps per meter. So, and at very, very far fields, we have really the wave impedance being at 377. Most of the work we do is in the near field. So for the very, very infinitely large plate, for the near field, the equations now are basically, as we can write them this way. For the reflected electric field, we start off high, and again, we decrease over frequency. And for a dominant magnetic source, again, we start off low and increase as a function of frequency. Okay, so this is the shielding effectiveness, the reflection for electric field source or a magnetic field source. So this is again what I showed earlier. And so this is for a far field and a large plate. When we're in the near field, again, if it's a magnetic source, the shielding effectiveness for a magnetic source starts off low and then increases. For an electric field source, we start off high at low frequencies, and it decreases as we increase in frequency. And again, these are for distances of 1 meter and a distance of 100 meters. Distances of, for example, 10 centimeters will provide a shielding effectiveness along this line for an electric field source or a magnetic field source. So if we look at a large, infinitely large plate, the near field looks like this. This is for a typical far field plane wave, but our magnetic source starts off low and it takes off to higher frequencies. And our electric field source is, again, decreases and then it increases exponentially. So again, this is for a combined absorption and reflection shielding effectiveness. So, for the electric fields, we could see that because we're relying on the reflection of that electric field, we can rely on very, very thin walls to give us most of the shielding attenuation. However, for magnetic field sources, we need the material to be thicker to be efficient, because the reflection item is low at magnetic field sources and therefore much more difficult to shield. So, summary on the shielding theory: shielding effectiveness for infinitely large plates is very high, as we showed, but that's not the world we live in. We live in a near field world, so basically shielding of dominant magnetic field starts low and increases with frequency. For the plane wave and electric fields, we start off high and it decreases with frequency. So to shield for magnetic sources, we have to think about the thickness of the material and to have high permeability of that material. For electric and plane waves, a thin material will be most of the time what we need to reduce the electric field of coming out of sources or protect components from external electric fields. So for example, you could put a piece of iron around a switch mode power supply to reduce its magnetic emissions. For electric fields, you can use a thin piece of gold material or aluminum on glass window to eliminate the electric field emissions. So, like I mentioned, we learned about the shielding effectiveness of infinitely large planes. In practice, we have to consider apertures. Our boxes have apertures, have feed-throughs, have windows, have slots. So we have to think about that. Every time we have an opening, our shielding effectiveness is reduced. And so we have to be aware of these situations. So I'm going to go through several shielding materials and examples. To shield, for example, against electronic components, conductive coating with conductive fillers in composites, yes, they're lightweight, they reduce cost, they're easy to apply. So these are very good shields. They're good for far field and plane waves, near field electric fields, but not for magnetic fields. And so usually data sheets are given for a certain material that show the shielding effectiveness. You got to be careful because you also want to know how well does that material do with magnetic shielding effectiveness. So most of the data sheets that you get just show the electric field. Be careful. You also want to know the magnetic field shielding effectiveness. In this case, this example shows the shielding effectiveness of silver, silver-coated copper, and nickel. Okay, it starts off high and then it decreases, which is typical for a electric field. So one way to find out if you have a very good shield is by doing surface resistivity testing. Basically, you can make these measurements in ohms per square, and there are typical tools that are used to measure the surface resistivity, and whether it's a 1 inch by 1 inch, 2 inch by 2 inch, or 10 inch by 10 inch square, you get the same results, the same outcome. So basically, if you select a material and it has a resistance at very low levels, you have high shielding effectiveness. So for low resistances, you have very good shielding effectiveness. For high resistances of that material, you have very low shielding effectiveness. So this is key in determining what type of material you want to use. You don't want to use something that it's in the kiloohms or mega ohms. You want to use something in the milliohms range. So other non-traditional materials, vacuum metallization. Basically, we use indium tin oxide for our solar cells to give us a good conductivity on the glass. Connectors can also be vacuum deposited with aluminum. Even your, I don't know if you've seen ESD sheets or ESD covers that have a vacuum deposited aluminum. Those are angstroms in thickness, and yet they're still very good electric shields. You could also use conductive paint. I bought a can of conductive paint, sprayed the inside of a plastic container because I wanted to make it into a good electric shield, and it worked very well. It's basically just applying this conductive paint on the surface of a non-metallic component. And those gives you surface resistivity in the orders of somewhere between milliohms per square up to hundreds of ohms on graphite. And electroless plating is another option. We've used containers of fiberglass material, dipped them and electroless plated these with nickel and silver, and we got very, very good shielding results. Other materials is embedded plastics with conductive fillers, such as metal or carbon. Right now we're doing studies at JPL to see if we could actually improve the shielding of this material by embedding them with conductive fibers, and those are working very, very well. Other materials, for example, in this case, is thermoplastics' Premier, gives you 85 dB of shielding effectiveness. Wherever there are apertures in a box, you also want to consider screens. You may want to vent that box, you may want to have an aperture or some sort of a see-through to look at LEDs or displays. To actually cover that hole, in the past we've used a mesh, metal mesh over HEPA filter apertures. On the Mars Science Lab, we needed to have a HEPA filter of roughly about a 10 centimeter by 10 centimeter square. Of course, we didn't want to have that big, huge of a gap, so we added a screen over that large hole to ensure that none of the electronics inside the rover leaked out of that large aperture. There's also conductive fibers. Conductive fibers in the form of conductive cloth. We've actually flown metal cloth when we found ourselves in a situation where we needed to shield a box at the last minute. We actually had our thermal blanketing people stitch together and form a shield made out of conductive fabrics to place around the box to minimize the radiated emissions, and we were quite successful in that. And just like building a toaster oven cover for your toaster oven, we ended up doing the same thing, except for our highly sensitive avionics that we needed to shield, and so we ended up flying a conductive cover over that avionics. RF tape can also be used. RF tape, like I mentioned again in the Mars Science Lab, where we had gaps, we bridged that gap using conductive tape. Problem solved. So you want to maintain emissions within a shield or protect your sensitive electronics from external high magnetic or electric fields using shields. So that's why we shield. And so typical boxes like cabinets have apertures. They have corners, sharp corners. They could leak out of flanges. In a real life situation, we have all these things that we have to be worried about. And each corner where there's significant amount of leakage, it's because there's a high concentration of compensation current which cause leakage. Or there are leakage due to flanges around a box. We also have resonances within a box that amplify the electric fields within that box and therefore amplify the leakage of that box. So here you could see a typical box with, it could be a dominant magnetic source with this type of a profile, and at high frequencies we have resonances, or it could be a dominant electric field with this type of a shielding effectiveness with resonances at high frequencies. Apertures, essentially you have a hole if your half wavelength is equal to the length of that hole or diameter of that hole. So one way to reduce the leakage and increase your shielding effectiveness is by adding multiple slots for a given amount of the same area for a slot. Or an array of holes like this are typically built on our spacecraft because we need to vent upon launching our boxes. We have to vent out and depressurize. So we have an array of holes to do just that. We can't fly a big hole because that's where leakage occurs. So we get around that by adding venting holes, just as displayed here. Honeycomb aluminum or waveguide beyond cutoff. You can make a long cylinder also to increase your shielding effectiveness. So here you have an essential filter made out of this cylinder versus just a hole, which is less effective as a shield. So here are honeycomb ventilation panels. If you have a fan, you have a need to vent, adding honeycomb panels is the way to go. So here is a metal case where if it's poorly shielded, if the lid just rests on the box, you will have a delta V, a voltage difference across that, where you have common mode currents bridging that gap across a high impedance path, which then cause electric field radiation. So a poorly shielded box with gaps will invariably radiate. So here you have slots across this box. And these slots will radiate. One way to get around that is by adding multiple bolts and screws so that you could cut off or reduce the gaps. Seams is another area where leakage can occur. Here on the Mars Science Lab, we had gaps all the way around the belly pan where RF leakage was occurring. We ended up bridging that gap by putting conductive RF tape all the way around, and we minimized the leakages coming from the inside of the rover. So when you do bridge and break a box through apertures, if you need to get into the box to carry signals in and out, make sure you have filters. Make sure you have overbraid with an EMI clamp. Once you have a wire through that gap into your box, you bridge that and made your box less effective as a shield, because E-fields will radiate out of that wire and not be as effective. So here we are with a box that will increase the shielding effectiveness with gasketing all the way around its connector and lid, and its 360 EMI back shell, and also a good back shell to chassis connection. So here are different gaskets. I won't go into detail. More gaskets. Gaskets are used to ensure that there are no gaps in your box. Typically, I like to use spiral type gaskets around my lid because that guarantees a very good seal all the way around joints. And it's been very effective in doing that. So I personally use a lot of gaskets in my box. So conductive polymers, conductive wrap polymers as well. Typical racks also have gaskets. Finger stocks are also used. These are quite delicate. In our high bay, we have a large door with finger stocks because our high bay is an EMI shield in itself, or EMI Faraday cage. But we have finger stocks running up 60 or 70 feet up and down the whole door. Those get broken or damaged because of the people running into them or not knowing that these are very sensitive, and they play around with them, so we're constantly having to change them. These are very, very delicate. So again, a very good shield, very good overbraid with EMI back shells gives you a good shielding effectiveness performance. you want to make sure that your overbraid is attached to your shield. A poor pigtail like this will produce radiated emissions. This is a no-no. You don't want to use pigtails anywhere because that will reduce your shielding effectiveness. Where you have joints, make sure you have dovetails or labyrinths to make sure that you just don't have two joints butted up against each other where you could see and have a gap. Again, various joints that you could use throughout. And again, don't don't minimize the fact that gaps will be a huge leakage path of your radiated emissions. Okay, so here a gap produces radiated emissions. Okay, good seals reduce radiated emissions. Okay, shielding and cables are very important as well. This is courtesy of Frank Leffering. He calls it the good, the bad, the ugly. Optical coverage is one way to take a look if you have a good overbraid. A poor overbraid with lots of holes is going to leak. A good overbraid with tight weave is going to be a high performer. So rules to remember: dominant magnetic fields use thick, high permeability material, mu metal, iron. Use high conductive material for other fields, electric fields. Reflection loss is independent of thickness. Key to high frequency shielding: aperture control, feed-through control. In the aperture, make sure that those dimensions are small to increase your shielding effectiveness. For more increase or have more smaller apertures and a big aperture to increase your shielding effectiveness. For feed-throughs, make sure your cables are shielded and terminated 360 around a connector back shell. Okay, thank you so much. So I have to run over to my next talk.